Hello everyone, welcome to the lecture on 3D computer vision. And today we are going to talk about absolute pose estimation from points or lines. Hopefully, by the end of today's lecture, you'll be able to define the perspective endpoint, or otherwise known as the PMP camera pose estimation problem. We'll look at how to estimate the camera pose of an uncalibrated camera with endpoint or line 2D, 3D correspondences. Then we'll look at three different algorithms of calibrated camera pose estimation, in particular the Grunet 3-point algorithm, the quant 4-point algorithm, and the efficient PMP endpoint algorithms to estimate the pose of a calibrated camera. Finally, we'll look at how to describe the degeneracies of the camera pose estimation problem. And of course, I didn't invent any of today's material. I took a lot of the slides and content of today's lecture from the textbook written by Richard Hartley and Andrew Zieserman, in particular chapter 7. This is for the case of the uncalibrated camera. And for the 3-point Grunet algorithm, I took it from the paper, which is a review of the original version of the paper, which is written in German, review and analysis of the solutions of the 3-point perspective pose problem published in IJCV in 1994. And I took the quant algorithm, the 4-point algorithm, from the linear endpoint camera pose determination paper published at TPAMI in the year 1999. And I took the efficient PMP problem, the ePMP problem and solution from this paper written by Vincent Lapetit, published at IJCV 2009. And the degenerate analysis, it's taken from the paper Space Resection Failure Cases, published at Photogrammetric Records in 1966. Now suppose that we are given a set of 3D points denoted by capital X1 all the way to capital Xn, defined in a world frame. What this simply means is that all these 3D points, which we write as Xn using a homogeneous coordinate, X, Y, Z, W, this set of coordinates, it's defined with respect to a assigned frame, which we call the world frame, represented by FW over here. And for each one of these points, we're also given its corresponding 2D image points, denoted by small x1 to xn. Now, what this means is that suppose that we are looking at this 3D point x2, we are also given the 2D image coordinate, which is the projection of this particular 3D point onto the image over here, which we denote as small x2 over here. So small xn in general would be also represented by a homogeneous coordinate x, y, as well as alpha that is defined in the camera frame, which we denote as fc. So we call this the 3D, 2D correspondences. Given this set of 3D, 2D correspondences, the task of camera pose estimation problem is to find the camera pose, which is the rotation and represented by the rotation matrix, as well as the translation vector of the camera frame in the world frame. So this is the objective. And this particular problem is also known as the perspective endpoint problem, or simply in short, the PMP problem. And the reason why it's called the perspective endpoint problem is because in this particular case, we're looking at the camera model where it's a projective camera model where all the light ray simply converge to the camera center, a single point of convergence. And in the later subsequent lectures, we'll be looking at what we call the non-perspective endpoint camera pose estimation problem. And in that particular case, we'll be looking at a general camera. A general camera could be any with a lens of any shape, where all the light rays simply do not pass through a single center of projection. Now let's start by looking at the first case where the camera is an uncalibrated camera, and what this simply means is that we have a unknown intrinsics value. The intrinsics of the camera is unknown, which we denote by K over here. As a result, what this simply means is that since the camera intrinsics is unknown, and our task here is also to find out the unknown rotation and translation of the camera frame with respect to the world frame, since all these parameters are unknown, so we'll simply put them all together into the camera projection matrix, which is a 3 by 4 matrix where 12 entries in the 3 by 4 matrix are unknown. So the objective now becomes we are supposed to find the 12 unknown parameters in our camera projection matrix such that the given 3D point, which we denote as capital X, is projected onto the given 2D point, which we denote by small x over here, with the camera projection matrix. And we know from earlier lecture in homography that we can, given an equation that looks like this, gamma xi equals to p of xi, in order to eliminate the unknown scale here, we can actually take the cross product of both sides, which is given by this guy over here, and simply equate it to 0. And what it simply means here is that the unknown scale can be cancelled out, since this is a scalar value that can be factorized out from this matrix multiplication operation, which is equals to 0. And expanding this particular equation over here, we will get this equation in matrix form, where the scalar value of x, y, and w here are simply the entry of the 2D point, and we'll simply rewrite or reshape the 3 by 4 matrix here, into a 12 by 1 vector. And this particular matrix over here is simply 3 by 12. And similar to the homography case, we'll see that we have three equations here from our camera projection equation, as shown here. Only two of them are linearly independent. What this means is that we can simply remove the third equation over here and end up with a 2 by 12 matrix, multiplying by a 12 by 1 vector that will always give us 0. So this simply means that we end up with a homogeneous linear equation of the form of ax equals to 0. And given and 2D to 3D point correspondences, we can simply plug these known correspondences to find each one of these constraints in this particular matrix over here. And given n of these 2D to 3D point correspondences, we'll end up with 2n constraints that can be used to form a 2n by 12 matrix, which we call A. And this together with the 12 by 1 vector forms a homogeneous linear equation of AP equals to 0, where all the entries in the matrix A are known, and the only unknown in this particular case would be the 12 entries in our P vector over here. And given a homogeneous linear equation that looks like this, where A here is 2n by 12 and P here it's 12 by 1. This simply means that we have 12 unknowns in this particular P vector over here. So in order for a non-trivial solution to exist for this homogeneous linear equation, the rank of A better be equals to 11, such that we have a non-trivial solution for this particular homogeneous linear equation over here. So since earlier on we look at this particular equation over here, where each one of the point correspondences gives us two constraints, and since we have altogether 11 unknowns in the P vector over here, well, what it simply means is that we need a minimum of 5.5 correspondences to get these 11 constraints, where the 0.5 correspondence here simply means that since each point, one point gives us two constraints, so the half point here simply means that we are taking one of these constraints from a point correspondences that is given to us. Effectively, a minimum of 6 point correspondences are needed, where the last point correspondence, only one equation is used to form the A matrix over here. And now the solution, after getting the minimal equation over here of AP equals to 0, we can simply solve for the unknown P using the right null space of A. So what this means is that we can take the SVD of A, which will give us uh, the left null space multiplied by the singular value multiplied by the right null space. And V here can be rewritten as the collection of the right singular vector, V1 all the way to V12. And the solution of P would simply correspond to the last singular vector in V, which corresponds to the least singular value in sigma. So in earlier lecture, we have seen that for homogeneous linear equations such as AP equals to 0 over here, to have an exact solution, the matrix A must be made up of measurements that are noise-free. And we know that in practice, this is not true because a camera is a real device that is often corrupted with noise. And this means that the data that we collected, which is the 2D to 3D correspondences to form the A matrix over here, it's always noisy. And in order to deal with such noisy data, we know that we have learned in the previous lecture that in general, we need more than the minimal number of point correspondences to compute the solution for this P vector over here. So as a result, here, it's always better to use more than 6 point correspondences. And the solution of the camera projection matrix can be obtained from either the algebraic or minimizing the geometric error, as we have seen earlier on when we look at the case of the homography. So to minimize the algebraic error, because we know that since A here is corrupted with noise, in general, you will never fulfill this homogeneous linear equation where the product of A multiplied by P will never be equals to 0. And so what we can do best would be to minimize the norm of AP such that it is as close to 0 as possible. And of course, if we were to naively minimize this the product of A and P, then we are not guaranteed to have a meaningful solution of P, because in this particular case, if we do not subject P here to a certain constraint, what it means is that a trivial solution could be found, and that would be simply to equate P equals to 0. And this is the solution that we do not want. So in practice, it's always good to subject this minimization, the algebraic error minimization, to a certain normalization constraint. And in this particular lecture, we will use the first option over here, where we will just constrain the norm of the vector P to be equals to 1. So this is similar to what we have seen earlier on in the lecture of homography and fundamental matrix. So in the lecture of homography, we do this where we want to minimize the norm of AH subjected to the norm of H to be equals to 1. And in the fundamental matrix case, this is what we do. We have AF over here equals to 0, and to minimize the algebraic error means that we will minimize the norm of AF and subjected to the norm of F to be equals to 1. Otherwise, all these cases here, by just doing this minimization without any constraint, then it's likely that the solution would be equals to 0. And this is what we want to avoid. So a second option here in this particular case, which is not applicable to what we have looked at earlier on in the case of the homography, as well as the fundamental matrix, would be to subject the normalization of the P matrix, in particular, the first three entries of the last row, which means that I have a P matrix over here. If I were to write it in this way, so this is the capital M, the 3 by 3 matrix, and this is the 3 by 1 vector over here. So P to the P3 over here, it means that I'm taking the last row of this guy over here. So M 3 by 3, the last row of this guy over here. and I want to subject the norm of this to 1. And the reason why this can be done is because, as we have seen in the earlier lecture, that the depth given x and p, p is the camera projection matrix, x is a point in 3D space. This depth here is actually given by the sign of over the determinant of m and multiply by w. W it's the, so if we were to project this guy over here, px into small x, and small x here would be given by x, y, and w. So w is the scale here that we are looking at in the image coordinate point, divided by t and the norm of m3. So m here refers to this 3 by 3 entry of the P matrix, and M3 refers to the last row of the first 3 by 3 entries in the P matrix over here. And T here, it's the last entry of the homogeneous coordinates of the 3D point. So we have seen that the depth is equals to the W, the sum multiplied by W divided by T, and the magnitude of the last row of the first 3 by 3 entries of the P matrix. And hence, in order to normalize this, we can subject the last row of the first 3 by 3 entries in the P matrix to have a norm of 1. And after we have solved for P using the SVD, we know that P here, the solution of P, is actually equals to a certain scale, lambda, which we call lambda, multiplied by the solution V. This corresponds to the least singular vector in the right null space, multiplied by lambda represents a whole family of solution for this p vector over here. So we can actually take the entries of this solved by one vector over here. So we can take the 3 entries that corresponds to this p3 over here and take the norm to be equals to 1. So this gives one equation in terms of one unknown lambda over here, where lambda can be solved. But in this lecture, we will stick to the first option here, although the second option here can also be applied. So after initial solution has been obtained from the algebraic approach, the next step would be to refine the solution using the geometric error. And the geometric error here is given by the reprojection error, where suppose that P here is the initial camera projection matrix that we found from minimizing the algebraic error. We can make use of this as an initialization to minimize the geometric error. And using this particular projection matrix that we have found earlier on from the algebraic error, we can project any 3D point X back onto the image, and which we call X hat over here. Since the camera projection matrix is an estimated one, what this means is that the reprojected 3D point onto the image, which we call X hat, it is unlikely to coincide with the measured point, which we call xi here. And hence, there is a certain error in between here. So this error is given by the Euclidean distance between the measured point and the reprojected point from our estimated camera projection matrix over here. And the objective now is that we want to find the correct projection matrix P, the 3 by 4 camera projection matrix, such that the total reprojection error for every point it's minimized, and this will guarantee us the best solution for the camera projection matrix. And in comparison to the algebraic error, as we have mentioned earlier on in our lecture in homography, as well as the lecture in fundamental matrix, is that the reprojection error, the geometric error, yields a much more accurate result because it's physically meaningful. We are actually physically minimizing this error over the prediction of the camera projection matrix. Whereas in the algebraic case, by simply minimizing this norm, there's no physical meaning behind this except for We are just trying to mathematically force this norm to be close to zero as much as possible, but we are not physically minimizing anything as the reprojection error that we are seeing here. And this particular minimization, we have also mentioned earlier on in the lecture of homography that this minimization can be done using uh, continuous unconstrained optimization algorithms such as Loewe-Marquardt. Another option would be to use the Gauss-Newton algorithm to do this. We'll see these two algorithms in more detail when we talk about bundle adjustment in the subsequent lecture. So since our objective is to minimize the norm of AP over here, subjected to the constraint that the norm of P should be equals to 1, we know from the lecture in homography that A here better be in a good condition such that when we take the SVD of A, it can yield a good solution for the P vector over here. But unfortunately, we know that A is made up of the 2D to 3D correspondences that might be defined very poorly with respect to the respective frame of reference. So for example, for the 3D points over here, we might be given a set of 3D points that are defined with respect to a world frame that is very far away from it, and with some of the points might be very close. And we can see that from the lecture in homography, we know that if this is the case, then we know that this would greatly affect the magnitude of the respective entries in the matrix A, and as a result, it will also affect the SVD result that is used to compute the solution for P. And we also know that this holds true in the 3D domain as well as in the image frame. So we might get some points that are here and some points that are here, and it's all defined with respect to a camera frame. So in this particular case, we know that the A matrix, it will affect the magnitude of the A matrix to differ greatly from one another, and this will in turn affect the results of SVD that is used to compute the solution for the P vector. So we also seen that in the homography lecture that a simple solution can be done to overcome this particular problem, and that would be to do data normalization. So in that particular case in the homography lecture, we are dealing with the 2D to 2D correspondences for case of homography. In that case, the data normalization would have to be done on the 2D domain for both of the images. And in our case here, we are given 2D to 3D correspondences. So data normalization naturally has to be done on both the 2D domain as well as the 3D domain. So in the case of the data normalization for the 2D data point, it will be exactly the same as what we have seen earlier on in the 2D homography case. So we have to define a transformation matrix such that all the 2D points in the image, such that the centroid of all this, let's say I call this centroid as C over here, to be translated to the origin or of the reference frame. And the points over here, in order to prevent this kind of situation where they are badly distributed in the image space, uh, we have to scale the points such that the root mean square distance, the total root mean square distance to the origin equals to square root of 2. And we have seen in the lecture of homography that this can be easily done by defining a scale factor, which we call S over here, to be equals to square root over the mean distance of all the points from the centroid. And similarly, we have to do the same data normalization in the 3D domain. We'll still do the same first step where we define a transformation matrix over here. So in the previous case where we define T norm over here, since this is in the image domain, this would be a 3 by 3 matrix. Now, since we are looking at the 3D domain, well, this transformation matrix, which we call U norm over here, would become a 4 by 4 matrix, where the first step of this transformation would be the same as in the 2D domain, where we want to translate the centroid of all the 3D points. Suppose that all these are the given 3D points. What we want to do here is that we want to, and suppose that this is the centroid that we are looking at in the 3D space, and this is the centroid which I denote as C. We want to define a translation such that the centroid over here is translated to the origin of the frame of reference. And next, we want to scale the root mean square of the 3D points such that the total root mean square distance from the origin or from the centroid is equals to square root of 3 over here. And this would prevent the case where we have some data that is scattered very far away from each other or very far away from the reference frame. And in order to achieve this, we will simply define a scaling factor over here, which we call S as before. But in this case, since we want the total root mean square distance to be square root of 3, then we can define S to be equals to square root of 3 divided by the mean distance of all the points from the centroid. So in summary, the pose estimation steps to estimate the camera pose of an uncalibrated camera with unknown intrinsic value can be summarized in this particular table over here. The objective here would be, suppose that we are given n points where n equals to or more than 6 points of 2D to 3D correspondences, which we denote as big X and small x over here. So we are given n points of this. The objective of this is that we want to estimate the camera projection matrix, which is a 3x4 matrix, such that from here we can actually decompose it to become the intrinsic value as well as the extrinsic value over here. This particular camera projection matrix should achieve the objective of minimizing the total reprojection error of every 3D point that we are given that is being projected onto the 2D image with respect to the 2D point correspondences that we are given as well. And we have seen earlier on that this can be done first by a linear method, which minimizes the norm of the of A multiplied by P, subjected to a constraint of the norm of P to be equals to 1. And this would be equivalent to finding the null space equation solution of AP equals to 0 subjected to P equals to 1. But before we do this, we also saw that the A matrix here has to be well conditioned by using the data normalization technique. And in order to do the data normalization, we have to do it in both 2D as well as 3D domain. So we have to compute a similarity matrix, which we call T, that we have seen earlier on how to compute this to normalize the points, and as well as a normalization matrix in 3D, which call U over here, to normalize the 3D points. So the normalization is simply done by computing this T matrix and then pre-multiplying all the respective 2D points to get X tilde over here, which is the normalized set of points. And we'll do the same thing for the 3D point. So after normalization, we minimize this by simply minimize A, P equals to 0, and by simply taking the SVD solution from A. And so once we have the initial estimate from this algebraic error, we can proceed on to refine the estimation of P using the geometric error, which is also the reprojection error. So here, what we want to do here is that we want to do the argmean over the camera projection matrix, all the 12 parameters in the camera projection matrix, such that the given 3D point reprojects to be as close as the corresponding 2D point as possible. And we can do this using either the Loewenberg-Marquardt algorithm, since this is an unconstrained continuous optimization problem. We can do this over Loewenberg-Marquardt algorithm, or we'll also see later that Gauss-Newton algorithm can also be used here. Then finally, in the last step, after we have obtained the camera projection matrix from both the algebraic initialization as well as the geometric error minimization, we have to perform the last step, which is the denormalization, to recover back the correct projection matrix with respect to all the original 2D to 3D correspondences that we have obtained earlier on. To do the denormalization, we will simply just multiply the inverse of the 2D similarity transform by the predicted camera projection matrix from the geometric error, and finally multiply it by the similarity transformation matrix for the 3D point denoted by U over here. And so after we have found the camera projection matrix P, we know that this is a 3 by 4 matrix, which is made out of the intrinsic value as well as the rotation and translation. And in order for us to reach our objective of finding the camera pose with respect to the world frame, which is essentially the rotation and translation, which is also the known as the extrinsic value of the camera projection matrix, we have to do a decomposition of the 3 by 4 camera projection matrix into the intrinsics, which is K, as well as the rotation and the translation vector over here. So we have seen earlier on in lecture 4 that this guy over here, the first 3 by 3 entries in our camera projection matrix, is actually equals to K multiplied by R. And what this means is that we can make use of M to recover K and R using the RQ decomposition. And once K and R are both found from the RQ decomposition, we can make use of the rotation matrix that is found in the RQ decomposition to find the camera center by simply equating minus R and multiplied by C. C tilde here is the inhomogeneous coordinate of the camera center, and with the last column of P that was found earlier on. So we can there are 3 unknown over here, and we have 3 equations. We can easily solve for all the 3 unknowns from this equation over here. And finally, what we also want to solve would be the exact solution for the translation as well. So notice that when we compute P from minimizing the norm of AP in the algebraic error, or even in the geometric error, that the scale is missing, because we say that we are subjecting this to the norm of P to be equals to 1. What this simply means is we ignore the scale of the camera projection, and this means that T here, the translation vector here, it's obtained up to scale at this point. That means that we do not know the scale of the translation vector here, and fortunately we are given the 3D points X. So each 3D point, we know its exact location away from the world frame over here. And what this means is that the 3D point gives us the absolute scale information, which can be used to recover the scale of the translation vector over here. And this can be easily done by looking at the ray equation that we have seen earlier on in the lecture. This actually means the set of points lies on the light ray. So X here is actually a light ray, where the beginning over here is the camera center, C, and the pseudo inverse multiplied by X. X is the image point over here, and if we will take the pseudo inverse multiplied by the image coordinate over here, we will get any point on this light ray over here. So X, which is the 3D point, actually lies somewhere on this light ray over here. So let's denote this by X. And in order to find, because we know this information from, we know X, the exact X, from the given 2D to 3D correspondence, and we know that this X here is parameterized by a single scalar value, which we call lambda here. That's the depth value over here. So since we know this, because it's given in the 2D, 3D correspondences, we can make use of this known value and this one equation over here that represents the light ray to solve for the unknown depth value. And once this is solved, we can put this back into the translation, because now the translation is without scale. So we can actually take t divided by the norm of t here and multiply by the lambda that we have obtained from this equation over here to get the new translation vector over here. Now, in the case where we are given line to 2D to 3D line correspondences, which means that instead of just now what we have looked at is that on the image we are given a set of 2D points, and we know its 3D correspondences, or also a point in the 3D space. We want to find the rotation and translation from here, which means that we want to find the camera pose. But now suppose that we are given a set of 2D lines. We are given all these lines in the 2D image, as well as its 3D correspondences here, which is also line. The objective would remain the same. Given this 2D to 3D line correspondences, we want to find the camera pose, the rotation and translation, such that the world frame is aligned with the camera frame. So as a start, we'll first represent the 3D line. Suppose that this is our 3D line. We'll represent the two endpoints, or any 2 points on this 3D line using a 3D homogeneous coordinate, which we call x0 and x1. And we also know that from the previous lecture, we know that a line back projects to a plane. So suppose that this is my line, x0, x1, my 3D line, and we have an image plane over here. At this image plane, it corresponds to a projection of this 3D line on the image plane. And we know that this particular 2D line, or this particular image projection, it back projects to become a plane. So in the 3D space. So this is the plane that is in the 3D space. And we also know that from lecture 5 that this back projected plane can be represented by the equation of P transpose of L over here, where L it's the image line, or the image projection of this 3D line. So this is the 2D line correspondence that we have over here. And we also know that this P transpose L represents the back projection of this 2D line to a plane in 3D space. And since we also know that the 3D line is supposed to lie on this particular plane over here, what it means is that any one of the two 3D points used to represent the 3D line, the dot product of it with the plane equation must be equals to 0, because there is a coincidence relation here between the 2 points and the plane formed by the back projection of the 2D line. So we can write this relation mathematically in terms of the dot product of the plane. So this first is the plane equation. We can take the dot product of the plane equation with any one of the 3D points, and that should be equals to 0. And now, since we get this equation over here, what we can see here is that each choice of j, which means that each choice of the 3D points, that is of the two 3D points that is used to represent the line, would give us a single linear equation in the entry of P over here. So what this means is that we'll get this equation where L, the 2D line, and the 3D point over here that represents the 3D line, these are known values, and the unknown is P over here. We can evaluate this into a linear equation, which is when we expand this out and then rearrange P to be on the right side and the L and X to be on the left side. We can see that it's simply a system of linear equations with respect to the unknown entries in the P matrix over here. And we also can verify this after we multiply it out. We will get this equation A of P equals to 0, where A here is simply made out of L, the 2D lines as well as the 3D points of xj, any one of the 3D points. And this would be a 3 by 12 matrix. And this guy over here would be can be reshaped into a 12 by 1 vector from the 4 by 3 matrix of the camera projection matrix. And similar to the last previous cases that we have seen in the point correspondences, as well as the cases that we have seen in the homography, that out of these three equations, only two are linearly independent. So we can rewrite this into a 2 by 12 matrix multiplied by p, which is a 12 by 1 vector and equals to 0. And we'll get the homogeneous linear equation here. So what this means is that given n number of correspondences, n number of 3D to 2D line correspondences, we can form a 2n by 12A matrix by stacking every two constraints from a single 2D to 3D line correspondence together to form the A matrix, where P here remains at 12 by 1, and this here represents the camera projection matrix, which is unknown here. And this is what we want to find out. So similar to what we have seen earlier on in the case of 2D to 3D point correspondences, we also want to minimize the norm of A multiplied by P subjected to the normalization constraint. So in this case here of the 2D to 3D line correspondences, we can also make use of either one of the two constraints. The first one would subjected to the norm of P to be equals to 1, which is the preferred choice here. And the second case that we have looked at would be to subject the third row, the last row of the first 3 by 3 entries of the camera projection matrix to be equals to 1. And so the in order to minimize this, we can apply the same technique that we have seen earlier on by taking the SVD of A. So this would be the left singular null space multiplied by the singular value and the right singular null space. And the equation, the final solution here would be given by the last column of the right singular null space that corresponds to the least singular value in uh, the sigma matrix over here. So once we have found the solution, an initial solution from the algebraic error, as before, we know that minimizing the algebraic error of given by the norm of AP here, it simply doesn't mean anything physically, except for we are just minimizing the mathematical equation such that A multiplied by P gives us 0. But in the physical sense, in geometric sense, there's actually no meaning to this particular error. So once we have found the initial solution for the P vector over here, which is a 12 by 1 vector over here, we will reshape it back to form a 3 by 4 camera projection matrix, and we'll minimize the geometric error, because now it's not a point correspondence anymore, and now it's a 2D to 3D line correspondence. So one of the way to define the geometric error is given by a paper which I have published a few years ago at the ECCV. So specifically, this geometric error can be as follows. So given a 3D line that is defined by the two endpoints xi0 and xi1 over here, we can reproject this two endpoints back onto the image, where this reprojected endpoints is given by x hat i0, that is directly computed from p multiplied by xi0, and we can do the same projection of this the second 3D point onto the image. And what we want to do here is that we know that the observed 2D line is given by this line over here, that we represent it as Li over here. So what we want to do here is that we want to minimize the closest distance that the reprojected endpoint make with the 2D line is represented by d0 on one end, and second perpendicular distance, which is made by the second point to the line, and this is also the closest distance from the second reprojected point to the line, denoted by d1 over here. Both of them should be as small as possible. And once d0 and d1 are 0, what this means is that the line that is formed by the reprojected endpoints would be lying exactly on the observed line, and this is the ideal case that we want. So in other words, we want to minimize the two errors over here. But we can see that there is a inherent bias towards shorter line. So if this line is very short, what this means is that the error that is formed by this would be smaller compared to a very, very long line. So if I have a very long line, a very small angle over here, it will actually make a very huge error at the two endpoints. So instead of just simply adding out the two errors of that's made by the endpoint, we'll also normalize it by the length of the 3D line. So as a result, this is what how we define the reprojection error for line correspondence.